Let's take a look at a couple of simple machines problems. If you're moving a refrigerator, you're moving it up a ramp to get it into a house. So we have a mass of our refrigerator, we have a ramp length, we have a ramp height, and we have the amount of force that the mover puts into it. So we've got all kinds of these numbers, and we have to figure out what goes what. So first of all, I'm looking for the work the mover does. Is that work in or work out? Well, the mover is putting energy in, so we're going to call that work in. We have a force, 496 newtons, and he moves it all the way up the ramp. The ramp is 2.1 meters long, so our mover does 1042 joules of work. Next part of the question, what work is done on the refrigerator by the machine? So the machine is going to do work on the object. So that's work on the object, or out. So the object is being lifted. We said when we're lifting something, then the force out is the object's weight. So we have 115 kilograms times 9.81 newtons per kilogram. That gives me weight. And how high is the refrigerator going? It's going 0.85 meters. So the machine does 959 joules. 959 joules of work. So now I want to find out the percent efficiency of the ramp. How good a machine is this? Well, I have work out and I have work in, so let's just use those ratios. Work out over work in. So I have 959 joules over 1042 joules. What I end up getting is 92% efficient. So that's actually a pretty good machine. If we look at this problem, we're moving a piano now up into our house, 6-meter long ramp this time rather than 2 meters, and I've got 1.15 meters I have to go up, so there are two distances, one distance in, one distance out. I have a mass of the piano. I'm looking for an IMA, first of all. IMA. All right, that's a ratio of distances, and I want it bigger than 1, so I'm going to put the big distance over the little distance. So that's 6 meters over 1.15 meters. And I get an IMA of 5.22. All right, part B, I'm using 3,700 newtons of force. I'm looking for the percent efficiency. Well, percent efficiency is going to be force out times distance out divided by force in times distance in. Okay, well now I have all those quantities. Force out, I'm lifting the piano, so that's its weight times its distance. So I have 450 kilograms. 9.81 newtons per kilogram to get me to weight, and it's going up 1.15 meters. Force in, they just finished telling me I need 3,700 newtons of force, and I am pushing it 6 meters along a ramp. So my percent efficiency this time is not so good, 22.9% efficiency. A lot more friction on this ramp. Now I'm using a pulley. Block and tackle is a big fancy pulley. I'm lifting 250 kilogram crate. I'm lifting it 85 meters up, so now I've got a mass and a distance. I exert 850 newtons of force. Okay, so there's a force, and I have a percent efficiency. So how far do I need to pull the rope? Well, 250 kilograms, so that's out. 8.5 meters, that's out. 850 newtons, all right, that's in, and that's all I have. So I'm going to have to use percent efficiency, and I have one term missing. That's the one I need to find. So I have percent efficiency is 72%. I turn that into a decimal, so 0.72. So I need the out stuff on top. So 250 kilograms, 9.81 newtons per kilogram. Distance is 8.5 meters. In, I'm doing 850 newtons, and I'm looking for DI. Okay, so there's my setup, there's my equation. I crunch through all the calculator steps, and I get a distance in of 34.1 meters. How many strands does the pulley have to support the load? Well, it turns out that the number of strands on a pulley is a good approximation of the IMA. So if I can figure out how many pulley strands are supporting the load, then I've got the IMA. Or if I can find the IMA, I know how many pulley strands there are supporting the load. So in order to find IMA, I need two distances. I have them now. IMA is my distance in over my distance out. I just found the distance in, it's 34.1 meters. My Distance out was given as 8.5 meters. So my IMA is 4. So that means I have 4 strands in my block and tackle holding up my crate. And that walks us through Chapter 5. And now you should be in great shape for tackling the problem set.